Hey everybody, it's Dr. Brizendine here. So what we're going to be doing today is we're going to get some background information on the stack and then learn about stack buffer overflow or just buffer overflow in general. Kind of get started in some low-level exploitation, and then we'll see some actual examples. So that should be pretty exciting. So we'll work on that. So understanding the stack is going to be essential as we delve deeper into software exploitation. So memory layout will be important to us. Fundamental aspects here is going to be the stack and the heap. Now the heap is going to grow dynamically going from lower to higher, which is going to be the exact opposite of the stack. Eventually, at some point, there is going to be an overlap. Potentially, most of the time, that simply does not happen. Now, the heap is much more vast in terms of size. Can accommodate many different data structures, large arrays. Those types of things are, by and large, going to be better served in a heap environment. We'll see that on the heap that we'll have things that are allocated, deallocated, so that actually needs to occur. A human being programmer needs to make the determination to do the allocations. Whereas on the stack, that's taken care of for us. It's managed for us. So whenever we involve the human element, that can invite opportunity for disaster. So if allocations are not done correctly, then that can provide fertile ground for exploitation. A lot of times programmers simply may not understand everything that is going on with the heap. They may forget about allocating and deallocating, particularly if it's a very large code base. Something may have been allocated and then freed at one spot, but somewhere very distant, there may be an effort to use again, resulting in a use after free bug. So as you can see here, our stack goes from a higher address to a lower address, which is really the opposite of what a lot of people may think. And it's kind of represented in a different way on IDA as well. So if we look at things on IDA, it may appear that it's growing because we have var plus 4, var plus a, etc., etc. But the plus is actually really a minus, a negative. The stack is nice for us because in terms of our variables, we don't have to worry about allocating memory and all that. It's taken care of for us automatically. The garbage collection is done for us automatically. When we leave the function and it goes out of scope, we no longer need to be concerned with it. So let's learn a little bit more about the heap here. The most important thing really is that as programmers, we are the ones who are responsible for management of the heap. We need to physically allocate as well as deallocate the memory, whereas on the stack, again, we don't need to worry about that. In terms of memory, it's going to be, heap is much less efficient, and we could even have things like fragmentation that may occur, whereas the stack is, of course, very efficient, deadly efficient with respect to memory. Scope, now when we have functions, keep in mind even main is a function. So the locals there are going to pertain just exclusively for that function. So if we leave the function, then it's probably going to go out of scope. That's typically the case. Whereas with the heap, things are global. So if we need for something to be present globally, then the heap may be a better choice for us. On the heap, we do make use of pointers. And of course, on the stack, there is no need for pointers. It just simply doesn't exist. So here we have an example of how we can have some code and how we can do allocations to make use of the heap rather than the stack, which is maybe a different way of thinking about it. So, typically when we would use a double or an int, we might do that on the stack. But, we could do it on the heap. And so we're actually allocating the region of memory with malloc, providing the size of it. So malloc, of course, needs the size, and we just do the size of double. So we create that. It exists on the heap, and we can modify and return that value. And then the same right here. So we have an allocation with malloc, another allocation with malloc, and then eventually at some point we free this memory. So we free age, salary in, and twice. If we were to go and try to use age or salary later on, that doesn't necessarily mean we're going to get a crash. More likely than not, it will result in aberrant behavior. So it'd be a use after free, a vulnerability, a memory corruption bug. Sometimes, I shouldn't say sometimes, but when you have a use after free, it doesn't necessarily mean it's going to be malicious in nature. There typically needs to be additional work that needs to be done to make use of a use after free in terms of using it as a vulnerability for purposes of exploitation. And we'll talk more about that at a later time. Right now we're focusing more on buffer overflow, providing some background information to assist us with that. So when we deal with the stack, there are two specific assembly instructions that are incredibly important for us in terms of how we manage control flow. What is control flow? Well, that tells you the direction that the instruction pointer is going to follow. Am I going to go from A to B or A to C? Sometimes we may take the stack for granted when we're working with our programs. We see call, we see ret or return, but we may not necessarily think about what they do. But they do have very, very important purposes with respect to how we manage that control flow. So when we go inside from one function to another, keep in mind, like I said, even main is a function. Then typically how we do that is we call a function. We make a call to some address. It could be an absolute call, where we have an address, or it could be an indirect call where maybe we're calling EAX or EBX. Either way, it's still going to take the address of the next instruction and push that onto the stack. And so when we go into that function, execute whatever is inside that function, at the very end, we will get to the ret. And when it returns, then it will go return to the next address on top of the stack. Well, guess what? The last thing that we put on the stack was the address of the next instruction. So the call and the return really is our mechanism for us to maintain control flow as we navigate from one function to another. Keep in mind some functions could call several functions before it finally returns to the original function that had called it. And so the stack can maintain all of that information for us, and so the program executes very, very nicely. Now, as we get a little bit more advanced in the semester and we deal with something like return-oriented programming or ROP, then we can make use of some of this to manipulate the control flow. So using the stack and using that property of return, where it automatically will go and execute the next instruction on the stack, that is central to ROP. And so it's very important that is even though we may take these for granted as being basic and simple, we absolutely want to understand them. And there can be other ways to address control flow. So control flows is making sure that our program goes where it needs to go, where we want it to go, whether it's what the programmer, the author intended, or if I'm an attacker and I'm making use of return-oriented programming, or ROP. Now, in my doctoral dissertation, I created a tool, the JOP Rocket, that made use of another technique called jump-oriented programming. And so that was an entirely different way of managing control flow, but instead of not using the stack and using calls and returns, we did it in a completely different way, which is beyond the scope of our discussion today. But there can be other alternative ways, but at this point, we just want to understand these and their importance. Some other things we want to start to learn about or refresh our memories on is EBP, Extended Base Pointer. So that will point to the base of a function. If we have variables, they're going to typically, if it's a Visual Studio, Microsoft compiled, it will make use of EBP. We can also use EBP to save ESP. So we go into a function. We want to save their stacks, save that ESP, and so we set EBP to ESP, and then we can make use of different arguments. We can also provide for the return address. Some great benefits of this is I can, if I'm inside a function, I don't have to worry about ESP getting all messed up because the old value had been saved. So couple other things, we can use EBP as the base pointer, so it can be pointed to the top of the stack when a function is called. Some things to be aware of if you have not encountered them or it's been a while is our prologue and our epilogue. So when we have a function, the very beginning of it is going to be the prologue, and at the very end is going to be the epilogue. So we take something like push EBP, we push EBP onto the stack, so we're saving that value. We can restore it later on. And then we take ESP and we move that into EBP, so that now when we're inside this next function that we're in, we can make use of ESP without having to worry about screwing up the previous ESP. And when the function ends, then we can restore ESP to what it was previously. And that value is going to be EBP. So we just move that back to ESP. And then the pop EBP will then restore what was previously EBP. So if I take a register and I push it onto the stack, then that will be at the top of the stack. And then at the very end, if I have pop EBP, that means whatever value is at this current time and execution is at the top of the stack.
As a noun, it is usually defined as a number of length equal to 1/12 of a foot, or alternatively.
Alexa, stop. Sorry about that. So, in any case, I'm not sure where I was, but when we have a pop EBP, we can restore whatever was at the top of the stack into whatever register that we specify. So if I said pop EAX, then the value would then go into EAX, whatever was on top of the stack. But my goal here is to restore EBP, so that's why it's pop EBP. So when we have EBP plus, then that can be our arguments. If we have EBP minus, and that's going to be our local variables. So when we look at things in IDA, it'll say opposite. So say EBP plus 4, EBP plus 8, or var 4, var 8. What it really means is minus 4, minus 8. And when we leave the function, when we're done with that, then the locals will be gone. They will be um, destroyed. On the stack, though, if we had been working on the stack instead, then they would remain unless they were explicitly destroyed. So another big distinction between the stack and the heap. So our local variables go bye-bye when we leave the function, but the things remain on the heap until they are explicitly destroyed. One thing to note here that we will see this quite often is when we do modifications to variables, to our locals, we're going to do it utilizing registers. So we'll move them to a particular to register, and then we can do whatever modification that we need to. And then when we're done, then we move it back to that local, which we see right here. A pretty trivial example here. So we have some variables, and then we see how that looks in IDA, and then we do some addition, and then the final result is then stored into varc. So 0, 1, 2. Then we add the values, and then the final result is then returned back to varc. So that will store it. So that'll be our x. Now, when you're working with things on the stack operations is going to be 10% slower than utilizing our registers. So of course compilers will optimize for use of registers over variables if possible. And the heap is even worse. It's even slower. And the 64-bit, then things do change a bit. We do have a much more frequent usage of registers. Some other things we may encounter that pertains to the stack, depending on the compiler, is going to be enter and leave. So when you learned assembly, it's possible that maybe you never learned enter or leave. It would not be surprising. So enter is similar to prologue, and leave is similar to epilogue. Now, when these were first created, when enter was first created, at that time Pascal was one of the predominant languages. And one of the cool things about that was that it featured nested functions. And enter 0, 0, the way that it's formed there is set up to make use of nested functions. So we could think nested if statements and then nested functions. If we think to a language like C or C++, well, the nested functions do not exist. So it's kind of an artifact, and we do see that quite a bit with computing in general. So enter is not used all that much, and when it is, it's usually done at a pretty basic level. So enter 0, 0. And then in the next slide, you'll see another example of how you could use it. Both of these are slower, so there really is not much reason to make use of it. Leave is going to be more equivalent to the epilogue. I think the speed is a little bit better than with enter, so we do see that a little bit more. One benefit, of course, is they're a little bit easier to write. So enter 0, 0 is what you would typically see, but you could also provide the first argument. So in that case, you could enter 8, so you're allocating 8 bytes, or 2 D words. So a D word consists of 4 bytes. A word consists of 2 bytes. So that would be equivalent to something like sub ESP8. So we're providing space for some locals. So again, leave, what it does is it will reset ESP to EBP, and then it will help us restore that original value of EBP. We still need to do the ret, so that is not included for it. Now, when we do modifications of the stack, we want to be cognizant of all the different ways in which this can occur so that we can recognize it and understand it. Some of these are instructions that you may have seen quite a bit. Maybe you've written code with them. You may think you do have an understanding of them, but as we get deeper and deeper into exploitation and work at a more low level, which we're getting pretty close, uh, we want to make sure we absolutely 100% understand these. So let's review them a little bit. So some of these will implicitly modify the stack or ESP. Some of them, this occurs explicitly. So implicitly, push and pop. We're adding to the stack with push. So push EAX, I will push whatever value is in EAX onto the stack. Pop EAX, I will take whatever value is on top of the stack. It doesn't matter how it got there. I don't care about that. And I'm going to pop it into the register that I specify. So pop EAX. That value goes into EAX. Call is going to take the address of the next instruction, push that onto the stack, and then it will go call that function, whether it's a virtual memory address, or it could be an indirect call like EAX or EBX, which may contain an address. It just is not available at compile time. It's done dynamically. And then the ret is the return. So at the end of the function, then we take whatever address is on top of the stack and we execute it. Now, the way that this is supposed to be done, the way programs were intended, it was that when we hit that ret, that's going to allow us to return to where we were previously. Of course, as attackers, because we understand how these work, we can take advantage of that. So if we gain access to the stack somehow and we place a series of 10 addresses, then it will go from one address, execute that, hit the return, and then go to the next address, execute all of that, and then return. So that's a great way for us to take charge of control flow. We'll dive into that much more deeply at a later time. Explicitly, so these are also modifying the stack. So we explicitly invoke ESP, so we add to it and move it, subtract it, and it, or other bitwise operations. And these have a direct impact on the stack. It could be exchange ESP EAX. So the address in EAX is now ESP. So in a sense, you could create kind of a false stack. And we'll definitely see how that comes into play later on in the semester. So again, just a refresher, it's simple but very important. These are our instructions to modify ESP. So we have a call and a return. So, again, call is going to allow us to save the next instruction to the stack, and then return will restore that next address from the top of the stack, or what is perhaps supposed to be, and I use suppose tentatively, and then enter and leave. We've discussed those as well. ESP based stack. Now, as we engage in exploitation, we may not always have the benefit of working with things that are compiled by what may be our favored compiler. So maybe we're used to working with Visual Studio, Microsoft compiled binaries. If it's compiled in a different fashion, then there could be an ESP based stack, which is fine. We just need to be aware that they're out there, that they exist. So they look and they feel very, very different. So right here, we're taking and modifying values onto the stack, and then we're saving values to the stack, and then we're taking our locals, moving them to a register. Keep in mind, once again, we get values into registers, and then once we do that, then we can perform operations on them, and then we do our addition. We're done. We take the result and we store it back on the stack, and that's the address. And here we have our leave. I don't see enter. It doesn't, if they use leave, doesn't mean they have to use enter. Enter is less efficient, so it's not used. But leave, they use leave. Now, if you're going to be trying to go and trace an ESP-based stack through a debugger or IDA, it can get a lot more challenging, a lot more confusing if you're having to deal with ESP-based stack. It's just harder for the human to keep track of things, really. Now, if you're doing something like IDA, I mean, you could of course make comments and whatnot to maybe assist you, but still, it is a little bit more confusing, perhaps. Of course, now when you have the CPU running it, it's no problem for the CPU to execute and deal with ESP versus EBP. And that's really what it's intended for. It's intended to be executed by the CPU, not for an analyst to go and read it. Stack cookies. If we don't know what stack cookies are, these are a great way to implement some form of security. So we could have the stack. The stack potentially could get overwritten. Buffer overflow is a classic example. Well, how can I try to stop and prevent this? Well, one way is a stack cookie or a canary or a stat guard. So I take this arbitrary little value, place it on the stack, and then if it gets overwritten and I can detect that change, then I know that there's been a buffer overflow, and so then I, as an operating system, could take appropriate action. If it's Microsoft and you're making use of the GS switch, then the program would throw an exception and you would error out. So depending on what you're doing, stat cookies are there for the program to ensure integrity, and so that can catch attempts at exploitation. So stat cookies, how do they work? Our stack grows from higher to lower, but the string, on the other hand, will go from lower to higher. So I have a variable here, a string variable, a buffer, and I overflow it. I overflow it by, let's say, 1,000. So it'll overflow EBP, it'll overflow the canary or the stat cookie, and then eventually it'll overflow the return address. So we take the stat cookie and we put it as close to the return address as we possibly can, typically. And so right before the return address, which will lead to EIP. So if the canary gets overwritten, then I know for sure that the next thing that would have been overwritten would have been the return address. So we can prevent that. How does Microsoft deal with that? Well, they provide a definition of the buffer being an array whose element is size 1 or 2 bytes, and where the size of the whole array is at least 5 bytes. Well, why is that important exactly? Well, it can come into play with variable reordering. But I think we probably understand the gist of it. So that's what's defined as a buffer. Now, a cookie is going to be a known stack value that will occur at runtime. So we'll have a D word, 4 bytes. And the cookie will be stored in the data section. We will take that and we will do exclusive OR, which is a bitwise operation, and we will perform that on EBP. And then we will then place that value onto the stack. And then when the function ends, we will then check that by doing exclusive OR once again with EBP. We'll see if it has been modified. So when the function returns, it will do exclusive OR the value with EBP. So our stack cookie into ECX, ECX, and then EBP. And then we make the call to the security check. So if there has been any modification, then when we do the exclusive OR, it will produce a different result, meaning the canary has been overwritten. Perhaps a good way to perhaps address this is through the use of a calculator here. So I can have a value like, say, well, that's actually, so we could do get exclusive OR and do 8 exclusive OR 5. So, oh, that did not come out right. 7 exclusive OR 8. I'm used to working on a different calculator for that. And so if I then take this and I do 7 exclusive OR F, or F exclusive OR 7, I will get 8. If I do F exclusive OR 8, then I will get 7. So let's check that out. And so that is indeed 7. So if you didn't know that that was one of the properties used with exclusive OR, that's something you absolutely do need to understand. So we see this quite a bit with particularly with malware, but we can also make use of this property with our exploitation. So there can be things called like bad characters or null bytes, and sometimes we'll have a stir copy could be our vulnerable function that allows us to get in there. Well, what's a null byte? It's 0, 0. So if I have 0, 0 in there, then it's going to stop copying it after the rest of that, and that could end my buffer. Well, what if I really need the 0, 0? Well, exclusive OR could be a way to do that, to get that to work. So just using exclusive OR and then other mathematical operations can enable us to get some of the values that we maybe not be able to directly place onto the stack or place at a specific location, but we can do other modifications. So make sure you understand exclusive OR if you don't. And then in another example here, we have a security cookie moved into EAX, and then we have that bitwise operation that I mentioned with EBP, and then we save the result of the security cookie into var4, and then at the conclusion, then we take that value here, which is var4, which is right. So then when we go and once we're done with that, then we do exclusive OR with EBP. And so then the value should be the same. It should be returned to what it was. If it wasn't, then that means var4 was overwritten, so stack buffer overflow. And so then we can abort the program. Here we see another depiction of how the GS switch comes into play with Microsoft. So we have a cookie here, we have a buffer, and then the buffer is we add a string. If we have a string to it, the longer it is, the more of this that will get overwritten. And eventually, if we go far enough, it will overwrite the cookie. Variable reordering is another thing that comes into play, and that's why our definition of what a buffer is important. So that determines how the variable reordering could occur. So we have a program here, or we have code here, and in this case we have an array, and in this case there's not an array. And this is a buffer. It meets the definition of a buffer. And if we look at this example over here, we see 0, 1, 2, 3, 4, which corresponds to all this. And we would think that the array would come next. So it would be var 14 plus 4, var 18, I guess. Um, but it's not. Well, actually, come to speak of it, it actually, um, so this is probably, the arrow there is wrong. So the arrow should be pointing to var 4. So it's really at var 4. Um, I don't know why I did this wrong. I may have been thinking security. Well, actually, I guess there is a security cookie there, so that does make sense. So we have the security cookie there, which was not prevalent before because it was not needed. Um, and then this value has been, the array has been moved over there. This way, if there is an overflow, then it's going to overflow var4. If it had been up here, which then it would have gone and overwritten some of these until it got to the return address. Or alternatively, they may have selected to say overwrite var14. Maybe var14 is used for something critical, and that may be the whole point of the exploitation, is just to override that value. So that prevents this from happening, the variable reordering. Okay, so that's that for the stack slides. We'll take a look at buffer overflow now. So we've encountered the idea of the buffer overflow and some of our various other discussions. At the heart of it, buffer overflows are very, very simple. They actually date back to the, I believe, early 1930s, maybe Air Force. They discovered it and they made a report on it, but that was not known. That information was not disseminated. And it was not until a FRAC article in about 96 or 97 by Adelphi 1, I believe that was the name, a pseudonym, actually, where buffer overflow was then revealed in the Smashing the Stack for Fun and Profit seminal article, or something to that effect. And from there, we saw various other articles that came about and expanded upon it. And so buffer overflow became very widely known, widely abused, and caught a lot of people off guard. And it took a while to fully address all of the security issues. And so that's where we got the idea of Stack Canary, Stack Guard, all of that, so that if there is a buffer overflow, then we can detect that, and then we can say, enough's enough. Let's stop this program and prevent some malicious activity from occurring. Is attackers mitigations like the GS switch? We can deal with that. There are ways to deal with that. Sometimes, not always. And various other mitigations came into play as well. So things like DEP, or data execution prevention. This idea that we have regions of memory that are either executable or readable and writable, but not both simultaneously. So it can't be executable and readable and writable. That's what DEP said. Now, I said the time frame for smashing the stack was 96, 97 or so, whereas when we have DEP being deployed in Windows, that's Windows XP Service Pack, I believe 3, so 2004, 2005, significant chunk of time. Does DEP directly address the buffer overflow? To some extent, it does. So, long ago, it could have been feasible in some circumstances to get code onto the stack. By code or shell code, I mean actual hex opcodes, the assembly instructions. When we compile our assembly, it's acting not on the mnemonics that we see, like add EBP3, but it's acting on binary. And so hexadecimal is just another representation of the binary. It's a much more convenient representation to say the least. But these correspond with different instructions, and where we start determines what they are. So if I go to a region of memory that contains hex opcodes and I start at point offset 0 and then start executing, then maybe that's the intended instructions. But if I start executing at offset 1 or offset 2, well, that may result in unintended instructions. Those opcodes may effectively turn into different instructions. And you can do that. That's one of the principles that ROP, or return oriented programming, works on. So getting back to the idea of depth. So shellcode is essentially hex opcodes. So we can take hex opcodes. We could have long ago placed them on the stack and just executed them. But now we have dep, and that says, the stack is readable and writable, but it's not executable. So you can put something on there, but if you try to execute it, it's not going to work. As an attacker, we can overcome dep, we can change it, we can modify that to whatever we want, and we'll see how to do that, and you'll have plenty of opportunity to do that. But perhaps we're getting a little bit ahead of ourselves. So prologue, epilogue, we know what those are. Stack frame. When we call a function, we will push onto the stack a stack frame. So EIP will then move to the first instruction inside the function. So our stack frame will consist of various elements that may be required by the function, such as our locals, our return address, our arguments. Now, speaking broadly of exploitation, we're trying to make use of unintended, strange, aberrant results and allow us to do arbitrary computation that may not have been intended, but is still possible. We don't care what the intention is, we just care if we can do it. So one of the first steps, not always, but oftentimes, is going to be to gain control of EIP. EIP is our instruction pointer that tells us what we're executing. If we can overcome EIP, then that means we can potentially take charge of control flow. We can say, okay, I'm going to go and overcome my mitigation. So if there's dep, well, why don't I change that so that dep doesn't bother me? Maybe I can make memory RWX, readable, writable, and executable. And now that I've done that, if I placed my shellcode onto the stack somewhere, and I've gone and I've changed it, so now I can execute it. So I get control of EIP, and then I tell the instruction pointer to go to different locations, to modify that, to get rid of dep, and then eventually to execute the shellcode. So high level, that's kind of where it's headed. And we'll see in the low level details of how exactly we do that. Of course, we need an entry point to overcome EIP, and vulnerabilities is what allows us to do that. So we don't necessarily want to get too caught up in the mechanics of how to execute and exploit once we have captured EIP. We also have to find the vulnerability to enable that in the first place, which is why we talked quite extensively about all the different ways in which exploits may be possible. I mean, it is to some extent trivial to think of certain commonly known vulnerable functions like strcpy or gets. Most of us probably have an idea that those could be used for a buffer overflow. That's low-hanging fruit. So hopefully some of our previous lectures have maybe given you insights into some other things that you could look for, other ways to maybe an initial vulnerability that may be non-obvious. At the end of this course, you'll get very good at doing some of the mechanics of exploitation but also want to make sure that we can find an entry point so that we can even do that in the first place. No, that's just one type of memory corruption. So there'll be other types as well. So heap overflow, we'll talk about the heap later on. Use after free, we'll talk about that as well. So having to deal with countermeasures as an attacker is something that we absolutely need to address. So buffer overflow is, a very antiquated method of doing this. I think a lot of us probably have an idea of what it is if we're involved in security and certainly taking a course such as this. But if we don't, that's fine. It doesn't really matter. But essentially, we were copying something from a destination to a source, and there is improper or no bounds checking, and so that then causes adjacent memory locations to be overwritten. Now, does that mean that it's going to lead to capturing EIP? No. Maybe our goal is just to overwrite a variable. We don't care about overwriting EIP. But again, it's just, we have a destination, we're taking some memory there, and then we're copying it to a source, and we're not doing bounds checking. Or it could be improper bounds checking, so it could be things like stir in copy, uh, where there is some bounds checking, and that bounds checking would be the third parameter. We could specify the length to copy. But if our source is, let's say 20 and our destination I'm sorry, our destination is 20 and our source is, let's say 1,000, then I go and do 300 for the third argument. That's still going to result in a buffer overflow. There is bounds checking, it's just improper. So what happens next? Well, it really depends on the mitigations in place. If there are stack cookies, then that may be it. But there could be other ways to address that, like structured exception handling. That could be something that could maybe be made use of. So the GS switch from Microsoft is one way to address that. I guess I should mention this here. So the program may crash. Now, as we're trying to discover some of these, that's probably a good thing for us. We want it to crash so we know that we captured it. But what if we had something like an actual legitimate address? Well, then it would go to that address, and then potentially maybe we wouldn't even notice that that happened. That's not a very likely situation. So if we're feeding it malicious input to cause a crash, we're manually fuzzing it, we're going to probably notice. That's the type of input we are going to use. As we develop it further, we will then make it so it does not crash. But initially, when it does crash, that lets us know that we can develop this further. Why do these occur? Well, we've talked about it quite extensively. Ultimately, it gets down to the idea of programmers are very lazy. They don't want to learn security practices. Nobody's taught them. It's not their job. They have deadlines to face, and there are more important things for them to worry about. It's somebody else's issue, not theirs. So they don't know about safe coding practices. Maybe they know they might know some certain unsafe functions like stir copy or gets, but maybe they try to use stir in copy, but they still use it wrong and it's still vulnerable. Or maybe one of the more esoteric mechanisms of causing an overflow could occur. Some of the things that we talked about in some of our previous lectures. So wide number of possibilities in terms of how it could happen. Security is not easy. That's why cybersecurity is such a hot topic, because there are a lot of people that are doing it wrong at every level, and certainly it does continue to improve. But there's still much more opportunity for it to do so. Again, it goes back to the idea of input. Any kind of input, any way a user is influencing what is going on to the program. They're typing something. It's an MP3. It's a picture. It's a text file. Whatever the case, something network based. It's all input, and it's not being handled safely. There's not a mechanism to validate it and to um, dispose of input that is can't be sanitized. And when a program gets to be very large, very complex, then it can be easy to lose sight of all the possible code paths that can happen. Some of this complexity could lead to some difficult to find memory corruption bugs, particularly with UAFs. So, how can we find a buffer overflow? Again, first we need a vulnerability. So, if we don't have a vulnerability, uh, then there's really no way to do any of this. So, vulnerability is a first step. Does the vulnerability lend itself to a buffer overflow? Maybe, maybe not. If it does lend itself to a buffer overflow, then great. We can see what happens next. You know, then we could engage in a process such as manual fuzzing to figure out exactly what we need to do to capture EIP or whatever it is that we may be doing. Um, Other alternatives is just trying to discover vulnerability. Again, some of this is review. If we have the source code, we could take a look at that. If we're doing fuzzing, we could do that. We could do our Peach. We could do AFL. AFL can also be done in a Windows environment and through other options. It could be done with anything really that executes in any type of code if you really want to put enough time and effort into it. So through fuzzing, we could discover vulnerabilities. Maybe we discover a vulnerability through fuzzing with Peach. It'll automatically execute WinDebug. It'll automatically execute executable or exploitable. We could take the results, we could take the input, we could investigate further and confirm, this really is a buffer overflow. So I didn't know about this before, but I found it through fuzzing. Then we could take that and then develop it once we understand how that happened. Enumerating all the possibilities for external input, and then checking to see again if it's handled safely, tracing it in IDA Pro, tracing it in a debugger. If there's any type of thing that's not secure, then that's an invitation for us to maybe make use of it. If we find a vulnerable function and we find a vulnerability inside a program, whether it's through IDA Pro or through source code, if we can't reach it with our input, if we can't influence it, then it does not help us. It is of no value to us. So being able to get to it, to reach it, is very critical. Stack smashing. So that's when the overflow occurs on the stack because again we don't have proper bounds checking, causing adjacent data on the stack to be overwritten, which may include a return address, allowing the attacker to then potentially take control of control flow, which is a bad thing. Sample program, you can pause that and think about it if you want. We're not going to discuss that. So manually fuzzing, how do we do this? Again, we want to look at so manual fuzzing, to distinguish from automated fuzzing, is where we're doing this one at a time. I'm opening up a program in WinDebug. I'm doing it, just trying it one by one to see what happens. Maybe I've looked at it, the IDA Pro, I've looked at it, the source code, whatever. I have some idea. I think I understand what's going on, so I don't feel that I have a need for a fuzzer because I can do it manually. I know I have a close idea of what's going on, and through some experimenting, I'll be able to figure it out in a relatively short amount of time. So that's what we're doing here with manual fuzzing. Now, scripts can allow us to help us in many ways. So we could use Python or Perl. In this class, I will use Python. If you know Perl, which I don't, feel free to make use of that. In the IA lab, I do provide you with the Cygwin Bash environment so that you can use that to interact with command line programs that we may attack, or just to generate things to fuzz. So that's the syntax there if I want to generate a lot of A's. So maybe B is my EIP. I could do it in that fashion. If it's a command line argument, so some command line programs make use of arguments, then we could do it using this syntax, and we can then supply one of the arguments, as you see right there. Now, if you want a little bit more flexibility, then we can just simply create a Python script or Perl script and then run that. In this case, it's being done through Cygwin. So we're interacting with this command line program. We're opening it, providing 20 A's, and then raw input saying attach the debugger. So this pauses. Really, it doesn't go beyond that until there's actual input. So it gives you a chance to attach your WinDebug or you attach your x64 debug before it closes out on you. And then the test, well, I guess it says test, and then it writes the A's right there. So what we're doing here really is, now that I look at this more closely, is asking for a password. So this first test right here is consumed by that. So it takes that test, and then it consumes the new line there. It terminates it. And then we do another one, which is our A's right here. And that's when we ask for entering the password. So it provides that, and then it closes out. So it's just another way to interact with it in an automated fashion, semi-automated, using a Python script, so I don't have to manually type all these same things over and over again. That would get really tedious. Detecting a crash, how we can manage that here. Whether it's WinDebug, x64 debug, Ollie, Immunity, we use the debugger to tell us that a crash occurred. And we specifically wanted to see not just a crash. So crashes, that may be useful, but not all crashes are going to be useful. We want to capture, at least for this buffer overflows, we want to capture EIP. So I'm overriding EIP with 43 or C, which is the value there. And it causes an access violation because it tries to go to 43434343, but there's nothing there. So that's hence the access violation there. If I wasn't using a debugger here, I may not know what caused the crash. I may not know what value was in EIP. So when you get deeper and deeper into the low-level development of exploits and software exploits, we interact extensively with our debugger or debuggers. So if you're not familiar with the debugger, you'll become more familiar, guaranteed. Another option is simply to examine the stack. So we could open up our IDA Pro, and we could just do a little bit of math, do some calculation, and see what happens. So we could do the distance between CC and var4, which is C8 or 200. var4 is going to be 4. S is going to be our save DBP, that's 4. And then our return address, our R, is 4. So I've 200 plus 4 plus 4 is 212. 4 bytes beginning at 208 will be the return address which will be returned into EIP. And then the 4 bytes at 204 is the EBP, which don't really care about that. And I have occasionally had one or two people get very hung up on EBP. We're focused here on the capturing the R, the return address. So keep that in mind. So how do I manually generate that code? Well, we could do a Python, and then you see the syntax there. And when I hit enter, then of course it generates all of that, and then I could select it and it'll copy it. I don't have to copy it. It's once you select it, it's automatically copied. Another nice feature of Cygwin. Of course, if you want to do work in the command line or another make Windows command prompt, you can set Python up there. But I just think that Cygwin makes it a lot easier to do just because you can very easily copy and paste. And that's much more difficult in a command line, Windows command line. So taking over control flow is going to be one of the focal elements of exploitation, one of our goals. And that's really just a starting point. At this point, it may seem like a lot. Oh my God, I captured EIP. Well, that's just the beginning. If all you can do is capture EIP, then maybe all you can do is just crash an application. We need to go beyond that, move beyond that. And sometimes that can be incredibly challenging. So sometimes that may be as far as we can get. So overwriting return address, different ways we can do that. Again, we can calculate the distance from input to EIP using things like IDAPRO, Binary Ninja, etc. And some people get very hung up on that, and if it doesn't come out exactly the way they think it should, maybe they give up. So sometimes if it's very complicated, maybe you're just interpreting it incorrectly. That may be a reason to maybe try another technique if you're really struggling with that. So one of the other techniques is just to send a large number of values, maybe 1,000 A's, and see what happens. If you get a crash, great. If you don't, maybe try 2,000 or 3,000. Now that said, don't try 10,000 because at a certain point it's going to cause another type of error. So you won't get the type of crash that you're after. So don't go too crazy. But if we do find it, if we do send 1,000 and we get our 414141, then we need to figure out where exactly. So if we eventually subdivide things enough, then that will then enable us to figure out where it was. I could subdivide to 500 A's and B's and then take B and turn that into 250 B's and C's, so on and so forth. If you do that enough times, like 8 or 9 times, then you're going to probably find it. Now, I don't want to see anybody, sitting there and typing the stuff into the whatever it is themselves. We want to use our tools. So use your Python, use your scripting languages to generate that input. Don't physically type and count that all by yourself. Another option provided by Metasploit as well as Mona is to make use of the pattern create and the pattern offset. So I could come up with 2,000 random values. And if I capture EIP, I could take those 4 bytes and then run pattern offset, and then that will tell me the offset. So it might say 704. So now I know how many to do. So there are different options that you can make use of. There's also online utilities that you could do that. So if you don't want to interact with either of those or you're not sure how, then maybe you might try something online. So you could Google search online pattern creator, online pattern offset, and more likely than not you'll find something appropriate. So stack pivoting. Now once we overcome EIP, then sometimes we may need to pivot not only to the shellcode but to other aspects of the payload. And this may make more sense as we actually do actual examples later on. So don't worry if you don't understand it fully at this point. But the idea is instead of just having a crash, all A's in your EIP, maybe you'll go to a memory address that will have an instruction that says uh, sub ESP 1000. And so then you go to a different location on ESP. You subtract 1000 from ESP basically. Well, if that's part of your payload and you have stuff there, then you're in control of that. So you subtract 1000, that was part of your payload, and whatever you have next in store, it will go and execute all of that. And I'm deliberately being vague here because I don't want it to get too crazy, complicated right away. But we'll look at how we can address things like DEP, data execution prevention, how we can bypass that, or how we can bypass ASLR. Or if we have stack cookies, how can we get around that? So stack pivoting is one tool in our bag of tricks that we can make use of. We can do it once, we can do it twice, however many times we need to do. And we don't have to confine ourselves merely to the stack. We could pivot to the heap if we're in control of that. If we have value, if we have content there that we're in charge of. Similarly, sometimes the stack is used for different API functions to provide parameters when those API calls, for instance. So maybe we will pivot to a false stack that we're in control of that has our values that we need to use. And we'll talk more about that at a later stage. Shellcode. So shellcode is, I think, important to understand. And maybe this slide could it may seem like a lot of information if you have not encountered shellcode before. But again, shellcode is position independent instructions, hexadecimal assembly instructions. And position independent means, if I'm a shellcode, I don't know where kernel 32 is. I don't know where ntdll is. And what are these? These are modules. So modules are DLLs. And DLL, the job is to export functions. So I'm kernel 32. I'm going to export wrappers to ntdll. So these are functions that can interact with the system. So that's my job is kernel 32. Well, if you're a shellcode, then you don't know the address of kernel 32, so you can't directly call that. But you can do other tricks and techniques to gain that information. So there can be something called the TIB. So FS register, FS0 points to the TIB. Well, FS30 will point to the PEB, the process environment block. Contains information about the process, including the DLLs that are in there. And we won't go into the details now, but you can make use of the PEB to find different modules like a DLL. And you could go there and eventually you could find the base address, the starting location. What is the starting location of a DLL? Well, guaranteed for every one of them is going to be MZ. It's the signature for a PE file. 4D5A, the hex content. Why do I care? Well, because that says I can now take the PE file format, which is a structure, and I'll apply it to this binary blob of content. And now I can walk the PE file format and I can find exports. Because the DLL, the job is to provide exports. So I can traverse the PE file format and then eventually find the export. So if there's a specific export I want, I can go in there and I can find the address for it. And so because shellcode is position independent, because it can't find these things on its own, we need to do little tricks like that by making use of walking the PEB in order to call upon functions that would not be available to us otherwise. So We can make use of any Windows API function that we want to make use of with shellcode. And we'll see more how to do that later on. But ultimately, we'll get the shellcode, hexadecimal content, uh, or hexadecimal bytes, and that's placed onto the stack. And as part of our payload, so maybe we have our EIP overwrite over here. Maybe this doesn't say it here. Maybe it leads to some other location where there's a stack pivot, and then we go and or maybe it goes and modifies the dep permissions, and then we stack pivot over here to the shellcode, which has now been made executable. So now we can execute it. And the padding, why do we need this? Well, because we need 1,000 bytes to cause the EIP overwrite. So the EIP overwrite happens here, and then we can store our shellcode in the shell and as part of the 1,000 bytes. But it needs to be, exactly whatever this precise number is, so that we can have EIP occur at a very precise location. So all of that is very good information to have. ASLR, address space layout randomization. So we randomize base addresses. We'll see how that comes into play. So that is very prevalent in modern Windows, where ASLR is used very heavily. We don't like that, so we want to avoid that. So we may try to use non-ASLR modules, or we may deal with a memory disclosure so that we can bypass ASLR altogether. So let's take a look at some actual examples.
Okay, so we're in a Cygwin environment, and again, if once you open Cygwin, you want to go and do something like this, and then you'll want to navigate to Cygwin Cig drive C, which I've already done, and then within here I have temp. So look inside here. I have a target. My target is going to be buffer overflow sample. So I have Windebugs set in the path so I can directly utilize that. If you haven't set that up on your own machine, that's something you would need to do. You can Google setting Windebug to the path. And I may talk about that more at a later time, but right now we want to just focus on what we're doing here. So do provide that here, and if we remember back from our slides, then we would do something like the money sign and then place inside parentheses, which I've done that there. And then we want to invoke Python, and then you do -C, and then place our content inside single quotation mark, so 1, 2. And then inside there, I could do things like print A. So let's do that. Let's print a bunch of A's. Let's print, I don't know, 800 of them and see what we get. And we invoke Windebug. And we look at our command line and we see, okay, this is what's on the command line. I have 800 A's. So if you haven't used Windebug before, I do have some of the on-campus students. They're producing some videos for you guys, so it'll help you to acquaint yourself with Windebug. And once they're done, I may provide some additional video material as well. So if it's completely foreign to you right now, that's okay. Just try your best. You can learn a little bit more about Windebug itself later on, and of course, just using it is going to let you learn about it a little bit more. So disassembly here, our registers here, memory here, value ESP, and then a command here, so we get messages. So when you open something in Windebug, it automatically inserts a breakpoint. A breakpoint is the hex CC, and the mnemonic is int3. It's an interrupt. And so it artificially induces that to occur. And so we hit G to go. and then we continue on. So it allows it to execute as if the breakpoint was not there. And so we did indeed capture EIP. We know this for two reasons. One, EIP, the address is right there. And then additionally, we look over here, and that's where it tried to go. It tried to go to memory location 41414141, but there's just nothing there. And so that's why it crashed. Now, if had this been a legitimate address, it would have gone to that address and executed what was ever there and continued along until maybe it would crash, maybe it wouldn't crash. Maybe it would not result in a crash at all. So we want to go a little bit further and maybe figure out how to capture EIP. So instead of 800, let's do 400 plus B times 400. Okay. And I got an error message. I saw string literal. And this is a mistake I made a couple times here before. But we need to make sure that everything is formatted correctly, and we lost that. So that should work for us. And now it's 4.2. So I had 400 A's and 400 B's, so that tells me it's in this region. And this message here, this box or prompt, just displays whatever output there would be, because this is, it's a console program. So I know I'm in the B's, so let's try to subdivide that further. And I'm doing the same thing there. And I'm still in the B's now, but now I know what's within 200. I'm doing my Control F and then X. I guess I could do the Alt F4 or whatever it is, but I don't really like using those as much. So it really just comes down to your personal preference. So let's try 100, and then do another 100. Of course, depending on how you're generating this is kind of a cumbersome process, manually typing it like I'm doing here, and it could be faster or it could be slower. This is a little bit slower here. And then I'll change this to D. And so now it's C. So 4.3 is C. And so I know it's in that region of memory, which is 100. And so let's do 50. Or actually, maybe we'll do something like this. Actually, I don't want to type that much, so we won't do that. Still in the C's, but now it's down to 50. And we can do 25. And we'll try plus D. And we'll change this one to, it doesn't really matter what we change it to, because it's not going to hit it. And I had some kind of error message here. This is not what I expected, so. Let's change these back to A, and change this to B here. So what happened there is it just may have been valid memory address. Is maybe what I'm thinking without diving into it too deeply. So I know it's in this 25 here, and so let's do 13 and 12. So now we're into the B, so now we're into 12, or that's that first pattern of B's there. And do 6 plus, let's do C. So we're still into the C's. And, you know, let's do it like this. So now we have uniquely captured it. So right here. So I could take all of these, add them up, 400 plus 100 plus 13 plus 6 plus 1. And then starting at that location then is what we would take to capture EIP. So that's really all we've really done here at this stage, is just allowing us to see how we could manually fuzz a program, how we could interact with a debugger, how we could use the debugger to tell us that we were successful in causing a crash. Now that we've captured EIP, then we could see what happens next. So this would be a good exercise just maybe for simple buffer overflow, just to allow us know that we were, successful. But as you can see, we really haven't done very much except to crash a program. So you might say, big deal. Well, as we can see later on, maybe it is a big deal, because we can go further and maybe cause it to execute shellcode and do whatever we want it to do. So it may truly become a big deal. All right, so that's all I have, and I'll catch you guys on Thursday.